Okay, so the plan for today is that I'll still tell you some more stuff about this convexity that we started discussing last time, and how is that relevant to finding the max and the means. That is what we are ultimately interested in. So let me just connect my iPad to the computer so that I can start writing. So yeah, I'll kind of add some more problems by the end of the week, and post some solutions to some of the problems. But like, it doesn't make sense right now before the submission time. If someone is getting stuck, you can email me, or I do have like office hours tomorrow. When did I make the deadline? Was it Wednesday or Thursday? Was it Thursday? So like, yeah, if not, you can also ask me on Wednesday before or after class. It's just like I kind of had a lot of questions in the other one, so that's why I kind of like got a bit too close to to the starting time. But usually I will get here fast earlier. Like, let me see if this cable works. But yeah, I'll post a few more problems like this week, and also our exam is in 2 weeks from today. So by the end of this week, I'll kind of give you like some sort of like guide of what you need to know for the exam, things like expectations, like topics and all that stuff. Um, I'm not using the cable share. That explains why I'm getting stuck. Oh yeah, it shows like I was not choosing the right one. Okay, now we're good. Okay, so let me hide myself. So here we are. Okay, so the idea of convexity that I was telling you about is that if you have like some sort of like region, which you also refer to as a set, okay? Um, well, a set is convex if you draw 2 points, right, which belong to the region. So let's color this region just to indicate that it would include all these points. And it has a property that whenever you draw 2 points, like the line segment between these 2 points is entirely contained in the region. So for example, if you draw these 2 points, this particular line segment is in the region, but if let's zoom in a little bit. If I take a point from here and a point from here, right, and I draw a line segment like this, then that line segment kind of like part of it is not, part of it is inside the region and other parts are not inside the region. So this particular set or region is not convex, right? So this one is not convex because it doesn't contain all the line segments. Between 2 points, right? Now, what I was saying last time is that when you have a region that's convex, and for us, the most important thing is that like all the problems where the optimization takes place will be convex regions. Like that's kind of what I was showing last time. So like, and I'll write that again in a bit. But the reason why I'm talking about convexity is that convexity will be true for like the regions where like the max or we're trying to find the max or the mean for the function. So they like convex sets have, or regions have, very interesting properties. One of the properties that it associated to being convex is that you can talk about its extreme points. Okay, so and that's kind of like I think where I ended last time. And the idea of an extreme point in terms of a picture is that it is a point that does not belong to any of the line segments that you can draw inside the convex set. So it is a point which is not part of any line segment inside the region. And I think I kind of gave you like the example of like the triangle. So like say if you look at a triangle, right? Let's see. Let's just create on, if you look at a triangle, let me put the color here. Look at that point. And so I could ask you, is the purple point extreme or not? And the idea is like, no, because for example, you find this point and this point inside the triangle, and the line segment through of connecting those 2 points like passes through the purple one, right? So in this particular case, right, the purple point is part of a line segment. Same happens, right, if you had chosen the point here, right? If you choose the point on that side of the triangle, like for example, choose this point and choose this point, and then there's this line segment, that connects them, that passes through that point. So far, so good. Is that making sense? But so you could ask, okay, and so in the triangle, what are the extreme points? They are literally the vertices, because if you think of a vertex, right? If you think of any of these three vertices, then that is good because of course, like the proof is kind of like if you were to try to actually prove it, not by a picture, like maybe that requires some more like thought how to write it down. But in terms of a picture, like there is no way to you can choose any 2 points on the triangle and draw whatever line segments that you want, but there is no way to when you try to draw the line segments, this point is not in the line segment of two other points, right? So like that kind of is what makes that extreme. Is that making sense? In like kind of the point, like the reason why I'm bringing up extreme points is because extreme points are the nice points for us. So this is what we're after. So we will be after extreme points. That's kind of like what the simplex method is all about. How do you find extreme points in a useful way? So we will try to find extreme points. So our goal is to study extreme points. Just as a remark, because since this is where the max or the mean will occur. This is where the max mean will occur. Just as a remark, like for example, if you look at a something like a disk, right? Oops, think of a disk. And then you are, that is convex. A disk is a convex set. The proof is not too bad, but it's also, if you do it algebraically, it is more, it's not as silly as you may think. It does require some like actual computations playing with inequalities, you know. Uh, Now, this is not something we usually like. We will have to worry too much about in this class because like this is not the type of region that will arise in our problems, because our problems come from linear inequalities or linear equations, and they usually have like sharper edges. Like the this is kind of like round, but it's still like if you just thought about like a convex region like a disk, just to try to understand what an extreme point is a little bit better. Well, if you think about it, in fact, any point on the circumference is an extreme point in the case of the disk. So let me put it. And again, like proof by picture kind of like hopefully makes it clear, but like of course, like trying to show that like more like algebraically can be trickier. So I'm not saying that it would be necessarily like an easy proof, but at any point on that like on the circumference is an extreme point of the disk, sorry. Which, again, like just for reference, like to those who like have taken multivariable calculus. So if you remember, like all these optimization problems in multivariable calculus, like on a bounded region, uh, you would have to find like critical points in the interior and also look at the edges or like the corners, right? The point is like because like in this class, like the functions are linear, there are no critical points in the interior, so the max or the mean can only occur along the boundary, which is what you would call. So that's kind of consistent here where like, the maximum and the mean could be somewhere on the circle. It's just that because of the function being linear, something better even happens here where it allows you to kind of like throw out the edges and just worry about the corners. So it's kind of like an improvement on what you would expect just from Calc 3, if you took Calc 3, because in Calc 3 you would only, the max or the mean could also occur like along the sides, but like, this is a bit better. So I'm just saying like, kind of we are in really the best of all worlds in the sense that we only have to worry about the corners, not even the edges, for like the types of functions that we will work with. Okay. So that is kind of like what I like, kind of like my general remarks about what convex is. Now the goal, and this is kind of like the the thing that makes this work all very nicely, is that there's like a very useful description of the extreme points in terms of linear algebra. Okay, so again, let me just going back to our problem, because maybe back to our optimization problem. So again, what we were trying to find, which I think like now I don't remember like the names for the farmers problem, but like we were trying to find like something like the max. Like I'll kind of just put some numbers in like before like writing it in the more general format. We're trying to find something like the max of 3x plus 5y plus 6z, subject to conditions, right? Like subject to x being non-negative, y being non-negative, z being non-negative, right? And then like let me put some inequalities, like like maybe x plus y plus z is less or equal to 3, and then maybe I don't know, like x plus 2y plus 5z is less or equal to 4, and then like I don't know, x plus y minus z is less or equal to 2. This is oops, sorry about that. This is a type of problem that we are looking into, like max or mean problems of like a function that depends linearly on the variables, right? All the variables are assumed to be non-negative, and the variables like satisfy like a system of inequalities. Now, what I was telling you before is that like the linear algebra conversion of this, right, is that first, like you think of this as a dot product. So this is like 3, 5, 6 dot XYZ, right? And this is like what we call the vector C, and this is what I'm calling the vector X for all the variables, right? And then these three together, you can, if you want to be fancy, you can just write it as saying that like this vector has to be greater or equal to the zero vector, because which again, like I think I have said it a few times, but just to bring that point, when you write like an inequality between vectors, the convention is like it is kind of like an entry by entry inequality. So that just means like x is like the first entry is the greater or equal to the first entry, and the second entry is greater or equal to the second entry, and the third entry is greater or equal to the third entry. So it's kind of like a simultaneous inequalities, like it's not just one. Yeah.
So does that vector like always have to be like a column vector?
Well, I mean, like whether you write them as traditionally, all the vectors are assumed to be column vectors, but like you can, whenever it comes, like here I didn't write it as a column vector just because it was easier for me to write it on like on the tablet that way. But yeah, I'm always thinking of them as being column vectors. For the once I get into trying to do like a matrix multiplication or something like that, they're like you do need them as column vectors. But if not, like, I could have read, like, it's just like, it looks weird because you have to put like a bunch of commas, if you write it as a row vector, but it would be more or less like the same meaning, like it would just be first entry, greater or equal to the first entry, etc., etc. So, but yeah, like usually they are secretly assumed to be column vectors, more like for this part of the conversion, because here, like you do want to rewrite this as a matrix multiplication, and for doing that matrix multiplication for the sizes to come out correctly, you do need the vector to be a column vector. So, like in this case, you just read off the coefficients, kind of like how you would do with the system of equations. If you remember how do you do like the reduction with Gauss-Jordan. So you would put 1, 1, 1, 1, 2, 5, right? 1, 1, -1, and then times x, y, z, right? And instead of equals, which is what you typically would have done, like in Gauss-Jordan, you just put less or equal, right? And this is what I'm calling the matrix A. This is again the vector X, which I really do need this one now to be thought of as a column vector for like this to make sense, like the products. And this is what you are calling the vector B, right? So in general, like all like our problems, right? All of our problems. So like or like our basic problem is can be rewritten as the max of a dot product subject to the variables being non-negative and this matrix inequality, which or vector inequality. So this is all that we're studying in this in this course, like all the oops, sorry, like I always forget to kind of drop down a little bit. Every single problem you could always rewrite in some capacity like this. That making sense so far so good? Okay, so now what I want to say kind of here's like what I'm going to kind of try to explain between today, like definitely by the end of the week. The idea is that if we had equality here, if we had instead like an equality instead of like an inequality, it is very easy to characterize the extreme points using linear algebra. Okay, so well, not easy, but it is possible. Maybe I'll use the word possible to not sound too biased. So it is possible to characterize. Okay. Because sorry, remember like I did prove this last time. The vectors that solve a system of equations is a convex set. Like I did say that last time. So this is like the vectors which solve this system is convex always. Um, In fact, also the vectors that solve like the inequality that like doesn't matter whether it's equals or less or equal to. The thing is like this particular convex set is very easy to find the extreme points when you have like an equality instead of like an inequality. Okay. So the first goal is actually there is a trick to rewrite every system with inequalities into a system just with equalities. That's the first magic part. So, which is what I want these variables, which are called slack and surplus variables, are for. So that's kind of like the first thing that I'll explain, how to reconvert any inequality into an equality. So so before like getting into this characterization. So there is a way to convert inequalities into equalities, at the of course, there is a price to be that you have to pay for doing that, which is you add extra variables. So like the price for working with equalities is to have like extra variables around. Okay. Mm-hmm.
Question.
Mm-hmm.
So we like did it graphically, but there was like no, was there equality?
No, the ones I did with the farmers, and the ones previously, I always wrote them as equalities. Sorry, as inequalities. So yeah, I didn't have like an equality explicitly. Yes.
Oh, so, but like the problem is that if there's too many inequalities, it becomes like time consuming.
Well, yes, although, well, if you were to do them by hand, yes, like that would be true whether, regardless of whether it's inequalities or equalities. Even if, think about linear algebra, if I gave you like a system of 10 equations, 15 unknowns, you don't want to do that, right? So like it's not whether it's inequality or an inequality, right? Like either would be time consuming for a human, right? Like on a machine, it's actually like even thousands of variables can be solved now pretty quickly with this simplex method that I still have to tell. It's more that when it's all equalities, it will be very easy to characterize what the corners are of the set, which is what we're trying to find. Like, yeah, yeah, yeah. Right, right, right. So it's more like, okay, regardless of like the problem, yeah, once you have a lot of variables or inequalities, you're like, you need to go to like a computer. That's not the issue. In fact, like before, like computers would become popular, they're like they would take days to solve one of these linear optimization problems. Like, people were called computers before, actually. That's where the name computers comes from, like with the army and all this stuff. So it would be like, then they would have like 30 people working on a single optimization problem. Right? It would take them like a week or whatever. And now it would take them like you to like 2 seconds just typing it. So uh but right, in all, regardless of whether it's inequality or equality, it takes time, except for like the problems that we will do because they're baby problems, right? Like, but like in the real world, I mean, but when everything is an equality, it will be very easy to say in terms of linear algebra what the corners are. That's kind of like what I'm trying to say. So that's why I'm going to spend some amount of effort telling you how to convert inequalities into equalities so that we can apply like linear algebra techniques. Okay.
Professor, but
Mhm.
so we like touched on con convexity. So we're not gonna like touch on it again.
Well, we will because we do have to check after I say how to go back, how to convert to equalities. I do have to say, oh, okay, these here's a way how to find the extreme points. And so I do have to use like the definition of an extreme point to check that whatever I'm claiming, which is called like a basic solution. Like, so there's a thing called like a basic solution, which is completely defined in terms of linear algebras, in terms of like a system of equations. So I have to prove that whatever is called like a basic solution corresponds to the same as like what an extreme point was before. And so there I do have to use like the convexity part again to show that that actually coincides.
Sounds good.
Yeah, yeah. So it's kind of like I will give like basically what I'm trying to say is that I will give a completely different definition of an extreme point, which has nothing to do with this one, and then I'll have to show that they're the same for like what the types of things like we want to work with. But so let me explain kind of like first, also just to clarify something about the maximum or the mean. Any max problem can be turned into a mean problem. That's actually like a good warm up thing to before like we get into that. So let me write this down. Like this is also like an important point to understand. So every max problem it is a mean problem and vice versa. And I'll say what I mean in a moment. So like this is step one. So like let me do like a graph, like a calc one thing, just to kind of like be a little bit more like general. Imagine I gave you like the graph of a function of one variable. I'll do something super easy because I have to reflect. Okay, so imagine I gave you like the graph of a function of one variable, and I ask you, okay, find the max. Just based on how the graph looks, right? Like you can think of it as being on a closed interval, it doesn't matter. It looks like this is like the value of x that yields the max, right? Let's call like asterisk, like actually. Like this is like the value of x that like optimizes the function, right? Where the max occurs. So this is where the max is. Right? And then, but now, oops. Now imagine that I turn the function upside down. By that, I just mean that I multiply by -1. So now like this is like the function y equals minus f of x. Like just multiply the graph like, by, it's kind of like, if this were like y equals x, then this one would be y equals -x, for example. That's what I mean. Um, or to think about y equals x squared and then doing y equals minus x squared, like, so that is how the graph for y equals negative f of x would look like. Is that making sense? Kind of looks plausible. And now, like the max became a mean, right? Kind of like looks, so now like this is where like the mean would occur, right? So what I'm trying to say is that so like just to write it as some sort of like equation, the max of f of x, if you are trying to find a max for f of x, that's the same as finding the mean for minus f of x, if that makes sense. And it goes the other way, but kind of works the same way. Like if you were trying to find the mean of f of x, that would be the max of minus f of x. Um, So what I'm trying to say is that if for some reason, you like just to go back, well, maybe first I should have stopped. Like, does that make sense? Like, so what I'm trying to say is that if for some reason you were kind of annoying, like in that sense, like you were, no, I actually don't want to see the word max here. I want to see the word mean every single time. Well, in this case, in this particular case, you could put a mean, but then you put a minus c dot x. You know what I mean? So you can always, like, you can always do like a trade-off depending on what is most convenient for you. It's kind of like an aesthetic thing. But if something has like a max, it can be turned into a mean if preferred. There's nothing like magical happening there. So it is more like what's natural for the problem in the real world. Like again, if you're talking about profit, you want to maximize profit. It is weird to say, well, maximizing the profit is minimizing minus the profit. Yes, that's correct, but doesn't seem like the most natural thing to say. But if you're talking about cost, it does make more sense to minimize the cost than maximizing minus the cost, which is the same mathematically. So it's more like the problem tells you whether you should set it up as a max or a mean, but mathematically speaking, you can kind of like translate between the two, without any issues, which is why, if you have been reading the book or if you read like many different optimization sources, usually kind of like sometimes like the standard way of writing it is involves a max or sometimes it involves a mean, but that's just one way to refer to it because it doesn't really matter which choice you make. The problem will just tell you which one, like again, like it's kind of like adapts to the problem because like there's no real philosophical difference between setting the problem as a max or setting the problem as a mean, if that makes sense. So that is, and again, like that is kind of like a good thing to kind of like understand first before like talking about the inequality stuff. Um, okay, now, yes, sorry.
I have a question, so, like, if we think about like the number, so the max would be like, for example, say like 50. but then the min would be negative.
Oh, right.
So we would take the absolute value.
Oh, I'm thinking more like, sorry, yes, like maybe, what I mean here is not, the value itself, rather where the point where the max or the min, yeah, yes, like but that's a good clarification, yeah. So the point that maximizes, the max is the same as the point that would minimize minus f of x, right? So for like not the, so let me put it here, but not the values, but the point, but the critical point, what you would call like the optimization point, right? The the but no, but that's good because like it does, I did write it like, not the values per se, right? Because as you're saying, like the values are actually reflections of one, or in absolute value, that is correct, right? But like it's more like, oh, this location is the same location. That's what I'm, and that's what we are actually trying to find, like the location itself. So no, but good. But rather the value of the value where the max of x, where the max for mean occurs. Yeah, that's what I meant. I mean, if you, yes, like, I think if you wanted to actually talk about the values, then you put like a minus in front of, like, which kind of looks too weird, but the max of f is minus the mean of minus f. So minus minus, like, it's kind of like a bunch of minuses, but then that fixes it. Or you just put it in absolute values, which is kind of like a more elegant way to do it. So yeah. But right, but in all this optimization, of course, in the optimization problems, you do want to find the actual value. But once you have like the point that generates the max or the mean, then you're good to go. You just plug in and then you're done. So really, like what we're after is like the point. Um, okay, no, but that's a good remark. And now, yes, let's talk about the inequality business. So um, well, first, which also like seems silly, but because we won't use it in this way, but it's also nice to, you know, you can convert equalities into inequalities, which is also useful to know. So like that's kind of like an easier direction. So like how to convert uh equalities into inequalities. It's a bit of a, like, again, it's not like the thing we're most interested in, but at least I would just mention it for because it's not too hard to explain, and for purposes of being like like go through like all the possibilities. So for example, if I wrote like an equation like 2x plus y equals 3, right? If I wanted to regard that as an inequality, you can write it as 2x plus y plus z is less or equal to 3, and 2x plus y plus z, oh, sorry, and maybe, well, yeah, let's put it like, and 3 is less or equal than 2x plus y plus z, right? So, like, it's kind of like I'll write it more algebraically, but it's kind of like silly if A is less or equal to B and B is less or equal to A. You know what I mean? So what I mean is like in any optimization problem, if you wanted, you can replace an equation by two inequalities. That's kind of going against, again, we want to go kind of backwards from inequalities to equality. So it's not something that we will ever really use, but it's kind of like theoretically, I guess, nice to know that you could if you wanted to, you know. So, but it's kind of like a two to, like, if you had four equalities, that turns into eight inequalities because like every equality gives you two inequalities, you see. So it's fine. It's good to know, I guess. But again, like no one really uses that, at least not for like the direction we're taking. Uh, the one that is more interesting, like like imagine like if I can put like a less or equal here, how do I turn that into an equality? That's like the cool thing to discuss. Um, so so what we want, and this is kind of like like I'll put that this is like the important one for us, how to go from an inequality to an equality. How to go from an inequality to an equality. So first um, well, I'll kind of like, let's so what you can do is like introduce extra variables. So, but I'll explain it first with an example and then like kind of like write it down more abstractly. But like once you kind of like understand it with an example, like it will make sense. So imagine if one of like the constraints was just like 2x plus y plus z is less or equal to 3. Okay. Well, basically, what does that mean? Like, like think about like, X, Y, and Z, they're variables, but they once you give them particular values, this will be a number and this will be a number, right? Well, this is already a number. But what I'm trying to say is that, like once you give X and Y and Z values, that just gives you a particular number. So just like imagine like drawing on the number line 3 and, you know, 2x plus y plus z, right? So the fact that like one is less or equal to the other just means like geometrically on the number line, right? Like this is like the number line. The like 2x plus y plus z is to the left of 3, right? Like that's what it means to be less or equal to. Okay, so far so good. Which means, and this is kind of like why it's called like a slack variable, because it's kind of like picking up the slack in the sense like there is like an amount that you could add to this to get to 3, right? And that will be just called like W, for example. So you introduce, so there's kind of like a difference between these two numbers, right? Okay. So you introduce a variable that kind of like makes up for like this like the gap between them. So to add a variable called W, and I'll do this in a more interesting example in a moment so that it kind of like looks like less silly, which makes up for the gap or compensates the gap for the gap between the two numbers. So it's almost like completely circular. Like it is almost like a circular argument. Like there's no magic happening. Like literally, if you want, you could. How would you find the gap between the two numbers? Literally, you would take their difference, right? Like you would say, well, what is the gap? Like what is the gap between 3 and 5? It's 5 minus 3, right? Like which is 2. So you just subtract them. But kind of like the convention is to always have like all the variables on one side, right? So the way you would think about this equation is like more like 2x plus y plus z plus w, that's the slack variable, equals 3. So this would be like the slack variable. But because again, it's kind of like saying like you're picking up the slack. So like, it's kind of like the variable that's helping us kind of reach the value 3. Of course, like when as x, y, and z take particular values, then the slack variable has to adjust itself to give you the equality, right? So that's why it's called like a variable, because, and you can see it here, like it just is whatever it needs to be in order to kind of like make the equation like the inequality into an equality. Does that make sense? Kind of like, and the idea is that just to make in a moment like a more interesting example, the idea is that there is a slack, you would do like a slack variable per equation. So, or sorry, per inequality. So you would do a slack variable per inequality. So just to do it just to do this in one of, sorry, just to give you a second, but let me copy paste, oops. Let me copy paste this one that I had written before. Uh, So the first thing here is that you do The first thing here is like you do need to convert this first to better notation because there are three inequalities. There will be needed three variables. Yeah, W would be fine if it's just like an extra one, but after W, what do you want to choose? Like you don't want to think about those things. So I would just relabel things so that this becomes X1, X2, and X3, right? X1, X2, X3, and then the extra ones will be X4, X5, X6. And then everything kind of looks a little bit more like on the unequal grounds because otherwise you will get into like what letters do I use and you don't want to like do that. So first I will just do the conversion to like nicer variables. Uh, but still in inequality version, okay? So this would become what? This would become 3x1 plus 5x2 plus 6x3, right? And then it becomes, right, let's do this. Like x1, x2, x3, they're all non-negative, right? And then let me just write the inequalities again. So this will become what, x1 plus x2 plus x3 less or equal to 3. And this is x1 plus 2x2 plus 5x3 less or equal to 4. And this will become x1 plus x2 minus x3 is less or equal to 2. Oops, sorry about that. So that is like the first conversion, kind of like to have like decent notation, like for the variables, original variables themselves. Okay. And then I have to do the same for, and then I do want to rewrite this without inequality. So I pick up the slack. So for each of them, I introduce a variable, x4, x5, x6. Okay. Let's see. Oops, like I should have copy pasted the other one. Um, okay, let's see. So like I'll do plus x4 equals 3, then plus x5 equals, sorry, plus 5 plus x5 equals 4, right? And then plus uh x6 equals 2. Okay? Is that making sense? Oops, sorry about that. Like I always keep forgetting. So far so good. And I'm missing something that I have to write explicitly in the optimization problems because the slack variables are supposed to be non-negative, right? Because like there are the difference between the upper bound and the lower, there are the difference. What are like secretly, if you were to think about solving for the slack variable, it would be the difference between the top value and the lower value. So that is always like automatically non-negative. So the new variables still kind of satisfy the condition that they're non-negative numbers. That's kind of why you introduce. That's also like one of the other reasons why you introduce them this way, so that they're automatically non-negative. But otherwise, it would be information that you're missing because if you allow this to put like a negative value, you're flipping the inequality, right? So like it's important to keep that in mind. Okay, let's see. Any questions about this? So we like originally, and I'm about to write this in matrix notation, but originally we started with three variables and well, I guess like three interesting inequalities. Now we have six variables and three inequalities. So like the number of like in the equation version of like this system, the number of variables like did grow, right? It's like so you have like the price for like changing everything into an equation is just like extra variables. So in terms of like the idea in like matrix format, what is like the matrix format for this? So now our vector would be x1, x2, x3, x4, x5, x6, right? Okay. You still want to see like the maximum as a dot product. So, but dot product, I'm thinking about them as being between vectors with the same size. So you just like add zeros as the last entries, like, the dot product, that's fine. So this is 3, 5, 6, 0, 0, 0. That's not much of a problem. So that now continues to look like max of C dot X. That's good. And then all these inequalities, like, x1 greater or equal to 0, x2 greater or equal to 0, up to x6 greater or equal to 0, can be written very conveniently, just like that the vector x is greater or equal to 0, right? Because that's just saying that every single entry is a negative, okay? And now, and then, like, now this is back to 50 linear algebra, right? Like, you have a system of equations. How do you extract a matrix and B, A and B from it? Just like read off the coefficients, right? So it is going to be 3 by 6, a matrix, because three equations, 6 variables, right? So let me put this like this. So it would be 1, 1, 1, 1, 0, 0, right? Then 1, 2, 5. There's no x4 in the second equation, so 0, then 1, 0, and then 1, 1, -1, then 0, 0, 1, and that is times x1, x2, x3, x4, x5, x6. That would give you the vector b. So 3, 4, 2. So the new a, that like the a we will work with, is going to be like what, 3 by 6 matrix, and this is like a 6 by 1 vector, so that multiplication makes sense, and the vector b will give you a 3 by 1. Oops. That making sense? So far so good. Questions about that? Is it clear, like, is it convincing now, like, how to turn every, like, inequality into inequality? Actually, let me do one more, like, baby example, because this is like, so basically your pictures are gone already, because even, okay, this one already was hard, like the original one was kind of hard to make, but it's doable if you work on GeoGebra, MATLAB, or whatever, because like it's in 3 dimensions, right? You can still do this region in 3 dimensions, but like, um, now if you wanted to draw this in 6 dimensions, that you're stuck, like, but at least I'll show. So I'll do kind of like the only thing that I can really do, like in terms of pictures, which is one constraint, but at least it will show you kind of what happens. So this is like the most basic example, but like it is the only one that I really can do. So let's say, just like the only type of picture. So pictures are more or less gone. Pictures are gone. But like here's like a baby example where like at least some like the picture survives. Let me see. I just want to make sure that I use the same numbers, because I'll be referring to this one like later for other classes. So just to make the numbers match to what I had before. Okay, and this is one like we can, it's so easy, we can solve it by the graphic method without any issues. But imagine I had given you you know the max of x plus 2y, right? And the conditions are that x is greater to equal to 0, y is greater or equal to 0, which are kind of baked into the problems always, and then that x plus y is less or equal to 4. Okay. So again, like if I put more inequalities, then I would not be able to draw anything. But at least here, first let me draw like the region without the slack variable. So this is kind of like the original picture for the region. So, you know, X and Y being non-negative, that just means like it's the first quadrant. This, how do you draw this on the plane? Like you draw the equality. The equality is like, what is the equality? It would be Y equals 4 minus X. Oops. Right? And then like the side of where the inequality is satisfied is this side. So the region corresponds to a right triangle, right? And there are three corners. Like we talked about that before, like a right triangle has corners, which would be 0, 0. This is like 4, 0, right? And this is like what, 0, 4, right? And of the three corners, kind of like by inspection, because you're trying to maximize X plus 2Y, of the three possibilities, like the one that maximizes that is like this one, because like has the highest Y value, right? So that one gives you max of 8. So this is where like the max would occur. And this is like the one that yields the max, right? We can call it like X max, or like well, X max. Is that making sense so far? So good. Question. And if I had written mean instead of max here, like with it also easy problems, like for the mean, with mean it would have been like the origin, right? Which is kind of like silly, but which is why I didn't want to put it. But actually, it's kind of like for so X max is for 0, 4 for if you're trying to find the max of X plus 2Y. And if I had actually instead like had given you like a minimization problem, like just like the mean of X plus 2Y, then it would have been the origin, right? Like so, but like the max is more interesting in this case, but like the mean can also be solved pretty easily. Okay, now, and again, this is like the one I'm doing this one, which is really, really dumb example because it is literally the only one that I can draw. So if I wanted to turn this into the standard format with equation versions, I have to pick up the slack, right? I have to add this slack variable here because there's a few variables. I'll just call it C, like, so in equation form, right? In equation form, what do we have? We have the max of X plus 2Y, and then X plus Y plus Z is greater or equal to, sorry, not greater or equal, it's just exactly 4, right? And then you have like that X is greater or equal to 0, right? That doesn't change. Y is greater or equal to 0, and Z is greater or equal to 0, right? And so the reason why I'm doing this example, which is very silly, is because this is the only example where like I end up in 3 dimensions, right? With 3 variables. And that's the only thing I can draw, right? Like, so, well, I don't know if you remember how to draw this, but this is like kind of like the equation of a plane, right? But you are only looking at the plane where all the variables are positive. So it's what you would call like the first octant. And the way that looks like, um, because now it is an equation, it is literally kind of like the region becomes like kind of like this triangle in 3 dimensions. So there's no like it is just like the piece, like it's kind of like that pizza slice. So but it's just that triangle. There's no inside, it's just like the triangle itself. Okay, because like it's now an equality. So the region, this is like the triangle. Not the inside, just the not just the surface. Oops. Is that making sense? And you know, what you can see here, hopefully, sorry, this is like the x-axis, this is the y-axis, this is the z-axis. It is kind of like interesting here to kind of keep track of where the max mean and were located because uh first, like, I don't know if you can see it, like if you kind of were to project, if you remember like how projections work from linear algebra, if you did that, you can project this triangle onto the xy plane, kind of like, projection by ignoring the slack variable. So the shadow that this triangle makes on the plane coincides actually with this region, right? So the projection gives you back the original region. So kind of like the extra variable, what it does is kind of like lift it up. You lift up the region into higher space. Like it's kind of like what you call like an embedding into higher, like, you're kind of like inserting this triangle into in higher dimensions, but perhaps like, it's still flat, but you kind of like maybe tilted or slanted a little bit. So like, I guess it could even change its area, I suppose. Yeah, that's fine. But so like the idea is like, but like it's kind of cool that, like the shadow is still kind of like the original thing. Like what you have to imagine is that if you had kind of like that's the thing, like if you had something in 3 dimensions, maybe it's more like a cube or something like that. You introduce extra variables, and maybe now this lives in 10 dimensions or 7 dimensions. But somehow, if you could look at the shadow into 3 dimensions, that would still be the cube again. So it's kind of like cute that that happens. And the other thing is that, that still has 3 corners, right? And they kind of like still match, you know, in this case, because it's very easy, it is easy to kind of to keep track to which corner each one corresponds to, right? So this was like, this would be 400, this would be 040, and this would be what, 004, right? So this 040 is where the max was occurring before. So that's still the max because it's still the same function. And now this is where the mean is occurring. So like the mean may look higher, right, than the max, but that's just because like we're not looking at the graph of the function, right? Like the graph is in 4 dimensions now, which is kind of like impossible to look. So now you cannot even look at the graph of the function. Like, it's just like the region itself. But this is where the max. So what I'm saying is that you still have 3 corners. So like it's not that the number of corners change or anything, right? It's just like the corners kind of work, like some of them kind of remain on the plane, but the origin kind of was lifted up. So essentially what you do took was kind of like took a triangle, you know, and you kind of like whoop, turn it like just move it a little bit. So, and again, what you have to imagine is that this is like the babyest of examples because I cannot do anything else. If I had 2 inequalities, then I need 4 variables, right? Even if it's a system, if I start with variables and I add two slack variables, I end up with 4. That's a picture in 4 dimensions. I'm stuck. So the only thing I could really draw for you is this one. And but that is already enough. Actually, you can extract a lot of intuition from here about what happens in the general case. So even though it's kind of like a very simple example, it does kind of like hides a lot of like what's actually going on. Because it tells you, okay, the shadow recovered like the original region, the corners kind of like match up in some way, etc., etc. So it's just that by putting it into this equation format, it is easier to understand like you know, what the extreme point, like the corners here. Like it's more easier for me to characterize these corners using like linear algebra. That's what I'm trying to say. Um, any questions up to this point so far? So good. Okay, so since we're almost done with time, I'll just kind of like say a few more things. Um, but I won't give all like the details, but like, and then I'll focus on this next time. So next time, what I'll do is kind of like, how do you identify those corners in terms of the matrix A? Like that's actually what I'm going after. But I'll just kind of like give you some like no. I'll just remind you in the next 10 minutes like a few things from linear algebra because I will use them for next time. So like it may be a good like moment to mention this because now we're talking about systems of equations, so I can kind of like say a little bit more about systems. So the first thing, like just to rewrite, so now we kind of pretend from now on, you pretend that, so now pretend that all the systems are in equation form, that we did this trick, we did the trick. And all the inequalities are now equalities. And all inequalities are equalities. Equalities. So how does our problem looks like? Our problem looks like you're trying to find the max of a dot product, right? Subject to the entries of this vector being all non-negative. And now we have an equation, right? So AX equals B. So in this notation, A is an M by N matrix. So that meant that it has M rows and N columns, right? And X is just like this vector of variables. So it's X1, X2, up to Xn. And B is like this, like, like the constants like that appear in the, in the system of equations. Okay, but the important thing is, like, again, there's no more inequalities for like the interesting ones. And again, like some of these could be slash variables or whatever, depending, like, if I didn't give you the system originally in equation format, okay? So assumption one, which is not like a terrible assumption, it's just kind of what I'll just finish explaining for the next few minutes. Assumption one, just to make our life easier, is that the rank of this matrix is the number of rows. So that's like the assumption that I'll make from now on. So my main assumption just is that the rank of A is the number of rows. So it's like what you would call like a full rank matrix. So this is like A is full rank. And why is that? Like, again, like I'll just kind of give you like a quick explanation about why you would like that. So I don't know if you remember. So I don't know if you remember how the rank works, but like the idea is like if you have like if you had like a system of equations, what would you do when you had like a system of equations? Like you would like how you would solve like the system of equations? You would do like this augmented matrix, right? Do you remember this? Like you would put the matrix vertical line B, and then you would do row operations to row reduce the matrix, right? So when you do row operations, you get some rows that are non-zero, right? Like that have like a number that's not zero somewhere in there. But then you could end up with a bunch of zero rows, right? So this could be zero rows. Right? And the rank was the number of non-zero rows that you get in the row reduced echelon form of the matrix, right? I mean, there are other ways to say it, but so the rank was number of non-zero rows. Is that okay? Is that making sense? And so what happens is that, you know, if the thing is like, okay, this is what you're doing, what you get with after doing operations to the matrix A, but you're also doing the same row operations of the vector B. So like the vector B also gets affected as you do the row operations. And then there's this chance, which is where the inconsistency could occur. If you remember, how do you identify if there's an inconsistent solution or an inconsistent system? Sorry, not inconsistent solution, but an inconsistent system is that you would get 0, 0, 0, 0, 0, 0, and then like a non-zero number here, or 0, 0, 0, 0, 0, 0, and then a non-zero number. So by having like the rank being not as big as the number of rows, you do risk running into inconsistent systems if this one, like if like these numbers do not become zero. So basically what this is doing is just like an easy way to prevent, like, rules out inconsistent system of equations, because if you're trying to maximize over an inconsistent system, there's no maximum nor minimum, there's no solutions to the system. So it's kind of like a very kind of like elegant way to kill off Because if you remember in linear algebra, there are three possibilities: either a unique solution, no solutions, or infinitely many solutions. Like that's the only three things that happens with systems of equations. So essentially, the rank condition kills off like the no solutions case. So it's kind of like just like a nice way to do that. So let me write that down. So and I'm almost done, I promise. So like if you remember, like I'll just throw that systems of equations had a unique solution, infinite solutions, right? And then and then no solution. But the condition on like assuming making that assumption of the rank prevents that from happening. So this won't happen of the rank condition. So far, so good. Everyone with me up to this point. Okay. And then what happens? That also tells you something else. Okay. Um, all also, so this is also something that you get for free. So also for free by assuming, let me put that as a, like, assuming like asterisk. And this is like the last thing I will write. Let's call this like some, or H for hypothesis. Hypothesis. Also for free by assuming H. Okay. How should I say it? Oh, so you may remember the rank of the matrix is the same as the rank of the transpose. That's actually one of the important things of linear algebra, right? Okay. But then okay. So and that is what if you remember, like with this system of systems of equations, once you know that, right? Okay. So at the same right. Like let me write it like this. At the same time, right? What is A transpose? So A transpose, if you remember, is like a matrix that changes rows with columns. So, right? So it's an N by M matrix, right? Right. So we know that because it has N rows, right? So it has N rows. So whatever this matrix was, its rank cannot be more than the number of rows. This we know for sure, right? Like the rank is always like bounded by the number of rows. So the rank of A transpose is always less or equal to the rank of N, right? But this assumption H, said that these two were the same, but our assumption was that the rank of A was already the number of rows like of the matrix A. So this was like has to be M, right? So what that means is that M is less or equal to N, or another way of saying is that for the matrices we work with, there are at least as many columns as there are rows. So in our systems, so for AX equals B, there are the number of columns is never less than the number of rows. So we're, so we have, or if you prefer to write it in more like, variables equations thing, we have like systems of equations where there are more variables than equations in general, or at least like, more variables than equations. I mean, they could be the same number, but you know, that will give you like a unique solution, and that's not interesting either, right? So our systems have more variables than equations, which if you look, sorry, just to go up, and this is kind of like the last thing I'll say now. If you look up for a second, if you think about how we turned the like, you know, like for example, where here. Yeah, like for example, if you look at the original one of these problems that I was working with, you had three inequalities and three variables. So here they were evenly matched. But once you turn it into equation form and you have to add the extra variables for the slack variables, that increases the number of variables, right? So in this case, you know, you kind of like augmented the matrix or like enhanced the matrix, and now you added more columns. Essentially, that's what happened. Like this was kind of, in fact, like this is like the original matrix of the problem, and then you add like the extra columns corresponding to the slack variables. So naturally, if you start with the system in inequality version and you start adding slack variables, what just would tend to happen is that you just end up with a matrix that just has like more columns than rows. So it's not like a bad assumption. Like I'm just trying to say, it's not like an assumption to be worried about. It's not like a unrealistic assumption, because even though in inequality form, it may not be the case that it would look like that. Once you turn it into equality form, then that's fine. And again, I'll use that next time, because once we have those two conditions, it's easier to talk about what the extreme points are for these things, and that's in terms of basic solutions. But let's just finish here, and then next time I'll tell you how the story goes, if that sounds good. So let me finish the recording.